Hey, my name is Yimu. I'm here to present our work with Sitao Zhang and James Wang from the Penn State University, learning emotion representations from verbal and nonverbal communication. If AI possessed emotional intelligence, it would advance artificial general intelligence. However, artificial emotion intelligence research lacks pre-trained models like those in computer vision and NLP. Conventional AI struggles with limited data using unrelated models. Insights from neuroscience and psychology highlights the importance of visual and language cues in emotion representation. Our paradigm learns directly from human communication, leverage consistency between verbal and nonverbal cues. By using uncurated data from daily communication, we overcome the limitation of data collection in emotion understanding. Incorporating verbal expression allows us to capture fine-grained details better than the existing dataset, as shown on some example images and the corresponding closed captions. We can already see the consistency between the visual and nonverbal cues. To address the challenges, we propose a new paradigm that directly learns from human communication, which involves collecting large-scale video and text data and a new model to guide the consistency learning. We gathered a large-scale video and text paired dataset from 3,600 videos of different TV shows, which translated into about 1 million raw video clips and corresponding closed captions. From the word cloud generated using those closed captions, we can already see some emotional cues. Then we process those clips, use the off-the-shelf models to group the word in the closed captions into complete sentences, assign a semantic scores to each sentence, and extract human bounding boxes. Our emotion clip follows the vision and language contrastive learning framework and focus on learning consistent emotion representation from both verbal and nonverbal expressions of the same individuals. The model consists of two separate branches of visual and textual input, respectively. The visual input are guided by subject-aware context encoding modules, where the textual input are guided by the semantic scores from an off-the-shelf model. Context encoding is an important part of emotion understanding, especially in an unconstrained environment, such as in the wild environment. As it has been widely shown in psychology that emotion process cannot be interpreted without context. To address this challenge, we propose subject-aware context encoding strategy, namely subject-aware prompting. Instead of introduce artifacts on the pixel space, which can cause domain shifts, we construct prompts in the latent space based on the positional embeddings. The positional embedding corresponding to each patch token of the subject is summed to obtain a prompt token, which provides positional hint about the subject location. As shown in the example attention maps, the attention from the prompt token gradually moves to the correct subject as the layer progresses from the left to the right. In contrast learning, similar emotion expression can lead to spurious relations since they are also repelled to each other. To address this, we introduce a semantic analysis model to guide the process as illustrated by the figure on the left. Using sentiment score, we surpass the false negatives and focus on emotion-related concepts. We analyze the approach by comparing models with different hyperparameters, as shown by the figure on the right. Increased beta suppress more negatives, improving the performance. However, excessively large beta hinder the training. One of the reasons is due to the unreliability of the off-the-shelf model. Another is the effect of reducing the effective batch size. Finally, we compare emotion clip with the state-of-the-art methods on several benchmarks dataset for both image and video input, including bold, movie graphs, meld, lyrics acid, and emotic. The table presents the result of those comparisons. Despite using only linear evaluation protocol, emotion clip achieves the SOTA or comparable performance against all other supervised methods using only visual input. Moreover, emotion clip even surpass multi-modal approaches that leverage audio and text descriptions in addition to visual information on some data set, for example, lyrics acid. It also outperforms vision and language model designed for general video understanding tasks such as video clip and X clip, which demonstrates our model's superiority in emotion recognition. In conclusion, we present emotion clip, the first pre-training paradigm for visual emotion understanding. Emotion clip opens up a new possibility for occurring emotion representation directly from accurate data, reducing the reliance on manually labeled dataset in effective computing research. We anticipate that our work will inspire future advancements in the area and foster the development of more adaptable and effective approach for visual emotion understanding. Thank you for your attention.